Okay, let's get started. So okay, so today we'll go over like Taylor's theorem. It's not really too bad, like, but let me just recall that, given f of x is sum k is 0 to infinity ak x to the k with radius of convergence r bigger than 0. So no r can be infinite. There's a theorem we learned previously that like taking derivatives, we could take it term by term, but not only that, the radius of the interval of convergence doesn't change, right? It has convergence on this, right? But then there's no reason to stop here, right? Like we can pretty much say just keep continuing taking derivatives, right? So so on and so forth, right? And then by same, whoa, what happened? Okay, so by same argument, like this thing converges on absolute value of x less than r, and so on and so forth, right? So you have the nth derivative is sum k is n to infinity. So again, we always shift index up by 1 because I mean all terms are infinite, but if you think about it, f has more terms than f prime because well, I can't shift. Hold on. Let me. Okay, because f has the constant term, and when you take derivative, you lose the constant term, so you sort of have one less term, even though they're both infinite. So okay, so from here, you can sort of see like what is the constant term? What is constant term of f prime? Yeah. So you see here, how do I get the constant term? Well, I plug in 0, right? Because any polynomial, like, I mean, if you just think of a polynomial, like, I don't know, 2 plus, I don't care what it is, like x squared plus 5x cubed, something, right? Just make it up. P of 0 is the constant term, right? And I mean, so if you think of a Taylor series, it's the same idea, right? I mean, when you plug in x equals 0, everything but the constant term goes away. So it's f prime of 0, but what is it? It's sort of, here the constant term is at 1, right? So it's a1. But you sort of need to divide by k, which is 1 in this case. And what you're going to sort of see is, because you're multiplying by k, so what you're going to see is fn at 0 is n factorial an, if you sort of think, right? Because like what term survives here? So if you look here, what's the constant term? The constant term is when, you have x to the 0 power, right? And that's when k minus n is 0. That's when k is n, right? And when k is n, this thing just becomes 1, right? N minus n plus 1. So, and when k is n, this is 1. So it's n factorial. So you sort of see that we actually recover every term here by the derivatives, right? The first one recovers A1. Obviously, f recovers A0 because you just plug in f of 0. But you sort of recover the coefficients of your series by taking derivatives. So f of x is sum k equals 0 to infinity. And so another way to write it is if you're given the top, it's given by this, right? So you need to divide out by k factorial to like cancel the, because you just have ak, right? You need to cancel that n factorial. So you need to divide by the n factorial. Okay, any questions so far? Okay, let me just check how many people. Okay, so note, this is the right hand, left hand side, and let's say this is right hand side. So let me just say, given a function, let me just say infinitely differentiable, right? So the right hand side makes sense. So now let me just put g of x just so we don't confuse it with f of x. We can make the series on the right, make the series the right hand side series. Yeah. We can always take derivative of, since it's infinitely differentiable, we take derivative of g, evaluate at 0, and then we form that series, right? So one can ask, does g of x equal this, sorry, x to the k. So remember, before I started off saying this is equal. If this is equal, then I could write it like this, right? But now the question becomes in general, okay, I can always write it like in terms of derivatives, but does it actually agree with my function? So it's like we're start going backwards in a sense. So does G equal its Taylor series representation? So is everyone clear with the question? Yeah. Okay. So before we continue, let me just say same result holds. Result holds for centered about C. I mean, there's no reason why you center at 0, right? So if f of x was actually equal to its power series representation, right? So f of x, this is certainly true, right? X minus c. Because you see, if I plug in c, I get c minus c, which is 0. So you see, I'm pretty much getting the constant term. So it's pretty much the same result, but like, you take your derivatives and you evaluate at c instead of 0. But of course, your series is different, right? Because it shifts by like x minus c. Okay, so how do we answer this question? Well, the series is just a limit of its partial sums. So you could determine how G differs from its partial sums, right? So in general, I can construct Rn of x is G of x minus. So let's just say we're you could take c to be 0 if you want, but let's make it arbitrary. Let's center it arbitrarily, right? So n minus 1, right? So here I take the partial sum at the n I guess, n minus 1 term, and I consider the difference, right? And if Rn of x goes to 0, I guess you could say if and only if, right? If and only if, you know, g of x is equal to the sum, yeah? Oh, why did I write f? Sorry. G. G k of c over k factorial. Yeah, so in other words, if and only if yes to question above, yeah? So this is normally called the remainder term, right? Because it's sort of what you get after taking out most of the finite ones. Because in general, if the series converges, the infinite tail is like small, so we call it the remainder. Okay. Any questions so far? Okay. So here comes Taylor's theorem. So I'm gonna give the the main statement. There's like an alternate statement in terms of integrals. I don't know if that's, I'm not gonna put that because I feel we didn't really go over integrals yet. I feel that that's like next chapter. So anyway, let's continue on. So f defined on AB, A less than C less than B. So of course, A can be negative infinity, B can be infinity. Yeah. And suppose, Fn exists on AB, and then for all x not equal to C in AB, there exists some y between C and x such that Rn of x is Fn of y over n factorial x minus c to the n. So why is this important? So let's just read the statement here, yeah? The Rn of x a priori, could be crazy, right? But it's pretty much saying my remainder is bounded by the next derivative. So you see here, I go up to n minus 1 derivatives, right? I mean, the sum goes up to n minus 1. So what the theorem is saying is Rn of x is sort of bounded by the next derivative. So we sort of, don't care about all the other terms. And so you can see here, this sort of looks like mean value theorem. So you can see like the proof involves, I guess, MVT/rho, right? I mean, it's really similar, right? There exists some y such that the derivative has that property. So yeah, okay. So why is this important? It's important because if Fn of y is bounded, I mean, let me just write Fn is bounded, then Rn of x goes to 0, right? Because I don't care what y is. If it's bounded by some n. And this thing goes to 0 as n goes to infinity, right? This goes to 0. Right, because no matter what x you choose, I mean, if x is c, I mean, x cannot be c, but if x is c, it's also true because it's 0. But if x is not c, there's just some number, right? Some number to the nth power over n factorial. Factorial wins exponential growth pretty much. And hopefully you all know that. If you need me to prove that, please type in chat or tell me. But hopefully it's obvious that exponential growth, is smaller than factorial growth. Okay, So if so one case is if, yeah, so okay, so let me continue. So they're they're sort of they sort of sidetrack, I guess not really sidetracking, but they go over some applied formulas. So this is for approximating roots. So for people who want to do applied math, this is useful. So there's something called Newton's method, where I won't go to this in detail because I feel this, it involves some calculator work and stuff. Find solution to f of x equals 0 with guess x naught. But the idea is important. So let me just sort of, show you. So here, you're sort of approximating. So if you think of math 2A, you've learned like linear approximation, right? This is pretty much linear approximation. You take a point close, the x naught should be close to x. So you take a point close to x, take the tangent line sort of, and sort of evaluate, you use the tangent lines to continuously approximate f of x. So so now xn 0 is line through xn minus 1 f of, so this is like a recursive formula, right? Once you know x0, everything starts. So the first thing you would plug in is n equals 1 with slope f prime of xn minus 1. And then there's a secant method. So I don't know, like, for people interested, I don't know what like the runtime is, right? 2 guesses. Like, I don't know what the, is it order of log, order of what? So secant method is given by xn minus 1 minus f of xn minus 1. Okay, so, but Taylor's theorem, it's pretty much approximation. So let me sort of explain the intuitive reason, on line through xn minus 1. Okay, so if you think of like e to the x, hopefully you all know the series, right? The question is sort of why do we need, this power? Why is it equal to power? So this series is sort of approximating e to the x in a sense. So one way to think of it is you've heard of math 2A, linear approximation, right? So you use tangent line to approximate the value of your function for points close by. But the point is, if you have like, e to the x, or like, I don't know, like some, natural log, these things are like, let me just write curvy. So you cannot you can approximate, but you can't get equal, right? Using just linear approximation, because linear approximation is just lines, right? There's no way you're gonna make straight stuff, into curvy stuff. So how do you get something curvy? Well, you go 1 degree higher. Yeah, you go from linear to quadratic. So you go to x squared. So this is like x, right? Or mx plus b. So it's the order is like x. So then you go to x squared to make it more curvy, x cubed to go, even to approximate even better, x to the 4th, so on and so forth. And eventually you need infinite powers to get equality. Yeah. So that's the idea. So Taylor series, it's just a bunch of approximations. it's like a generalization of math 2a. So I'm approximating, but to get actual equality, I need to use more and more terms, more and more powers. So, okay. Anyhow, let's continue. So let's start doing questions for today. So, okay, so we are sort of, find power series for cosine. Let me just say Taylor series. For cosine, and explain why cosine of x is equal to its Taylor series. I feel the second part's the harder part. Is equal to Taylor series. Right, so to find Taylor series, again, let's just assume, the book doesn't really say, but I mean, without loss of generality, you could just assume it's centered at 0. Yeah. Just to make stuff more convenient. So so how do we find the Taylor series? Well, the Taylor series is given by this, right? The right-hand side is given by this thing. So how do we, find it? Well, we just calculate. So a priori, there's infinitely many derivatives you have to calculate, right? So, the general pattern is, you should notice a pattern. Yeah, or else it gets pretty hard to write the series explicitly. So first is cosine of 0, which is 1, right? So I'm calculating f0 at 0, f1 at 0, right? And you calculate f2 at 0. And then, so on and so forth, right? So derivative of cosine is negative sine, and I'm evaluating at 0, so this is 0. Derivative of sine is cosine, so I get -1. Derivative cosine is negative, so I get sine of 0. And then you see we go back to cosine of 0, right? Derivative of sine is, sorry, there should be 1. But the process repeats, right? Because we had this right here. So you see, only what's the pattern? Only even derivatives survive, right? The odd derivatives have coefficient 0, survive, and alternates, right? So you can see that, if you just look at the pattern, it's given by this, right? It alternates, so I need a -1 to the n, but I only care about the even powers, right? So remember, it's x to the n, it's like, x to the k over k factorial. So if I replace k by like 2k, it becomes 2k over 2k factorial, right? So you see here, cosine's given by this. But sadly, power series is of this form, right? An x to the n, right? So this is sort of like, to write it in the power series form, let's write it like this. It's equal to sum n equals 0 to infinity an x to the n, where an is, if you just try to calculate the formula, you get this. An is for n even, and an is 0 for n odd. Yeah. So just reality check, if I plug in 2, right, this should be -1 to the 1 over 2 factorial, right? So the coefficient of x squared is when n is 2, right? Just reality check is n is 2, and that's, if you plug it in, you get a2 is -1 to the 2 over 2 factorial. So that's -1 over 2 factorial. Here, I'm just rewriting the series, but what is the x squared term here? It's when n is 1, right? Because it's 2n. So if I plug in 1, I should, you can check, you also get -1 over 2 factorial. Okay, so this is our series, right? So from here, we found the Taylor series, but now we have to explain why cosine is equal to it. That's the harder part. So that's where we use Taylor's theorem. So Taylor's theorem says, you know, the Rn of x, remember, so we're going to be using the fact that, where did I write it? Right, Rn of x goes to 0 if and only if you're equal to the power series, right? So to check that cosine agrees with its power series, we need to check Rn of x goes to 0. But Taylor's theorem tells us some nice thing about Rn of x, right? It's bounded by the nth derivative. Now, Rn of x is bounded by, you know, the nth derivative of x. So, but I need to fix an x. So let's let x be an R. Want to show cosine of x is equal to some. Yeah, so now x is like a fixed number. Yeah. So I need to show these are equal. And how we do that is we say, okay, Rn of x is, you know, equal to like the nth derivative. This is like f of x. The nth derivative at y for, and then where does y land? So let's go back. So y is just, in this case, it doesn't matter, but y is between c and x, right? Right here. So c is where we're centered at. So we're centered at 0. So we are between 0 and x. So for some y between 0 and x, y between 0 and x, fn of y over, I don't want to scroll up. So fn of y over n factorial, and then it's x minus c to the n, but c is 0. Yeah, so this is just x to the n. Okay, but I don't care what the, I mean, the nth derivative depends on, you know, where we are, right? Like it could be sine, it could be cosine, but I know it's bounded by 1. So this is bounded by, and this goes to 0, right? I mean, x is just a number. Again, exponential loses to factorial growth. So you see here, and x was arbitrary, so we get that cosine of x is equal to its Taylor series. Okay, is everyone clear on you know, the process of Taylor series right now? Okay, okay. So let's do one more just for practice. So there's something called the hyperbolic cosine. It's given by cosh of x. I don't know why it's, you know, denoted like this, but it's just shorthand for this function. Okay, so again, right, we need to, you know, sort of find the derivatives, right? So f0, let's say centered at 0. Yeah, make things convenient. Centered at 0. So f0 at 0 is what? Well, let's figure out what f0 of x. So f0 of x is just the original function, right? So if we at 0, it's equal to what? 1/2 e plus, 1 plus 1, right? E to the 0 is 1. So yeah. And then f1, it's just, you just have a minus sign, right? And at 0, this is 0, right? Because you get 1 minus 1. And similarly, you'll see that f2 gives you back the same thing, right? Gives you back cosh. So it turns out the F1 is actually sinh, right? I'm sure you all know derivative of cosh is sinh, derivative of sinh is cosh. So here, at 0, it's equal to 1, right? So what's the pattern? Again, only even powers here, right? Even powers. And all 1. So in this case, it's kind of like cosine, but you don't have that -1 to the n, right? Because your series doesn't alternate signs. So it's just this, right? And again, you can write the actual power series representation, but okay. Now y is cosh equal to this. So y is cosh of x equal to, right? Because here, this is just a series we formed from the derivatives, right? There's no reason to think it's equal to cosh. So let me just write it's the 2n over 2n factorial. Okay, so again, let's use Taylor's theorem. So let's let x be arbitrary number in R. And then Taylor's theorem says Rn of x is Fn of y over n factorial x minus 0 to the n. Yeah? Now, Fn of y, so let me just say Fn of, I don't want to use x. Okay, I'll just call this x tilde, yeah, because I'm going to use x here. So x tilde. So Fn of x is either 1/2 e to the x plus e to the minus x, or this, right? But in either case, this is smaller than, if x is negative or positive, I take the absolute value, right? So this is smaller than 1/2 e to the absolute value of x plus e to the absolute value of x. Yeah. And similarly, this is smaller than if I just add, same thing, e to the absolute value of x plus, because exponential is always positive. So, right? So this is smaller than or equal to just 1/2, or since I just add the same thing, it's just e to the absolute value of x, right? Is everyone clear on this? So for example, if x was -1, it's smaller than e to the 1 plus e to the 1 times the half. So, and then again. Okay, but this is just, so this thing, Rn of x tilde is Fn of y for y between 0 and x tilde, right? So a priori, I don't know what, y is, but I certainly know y is smaller than or equal to absolute value of x tilde, yeah? Because x tilde could be negative, but, I'm certainly smaller than the absolute value of it. So here, I could say I'm smaller than or equal to e to the absolute value, using what we had above, e to the absolute value of x tilde over n factorial x tilde to the n. And here, the e to the x tilde is just a number, right? Some number. So I have a number times a number to the n over n factorial. This goes to 0, right? Same reasoning. The number times exponential growth is exponential growth, and bottom's factorial growth. Yeah? Okay, is everyone good so far? So I haven't given you an example of where we are not equal to the power series, so I'm gonna do that now. So is everyone good so far? Okay, great. So this is 31.5. So g of x is e to the minus 1 over x squared if x is not 0, and in 0 if x is 0. Okay. So before I continue, hopefully everyone is convinced. So let me just write out the factorial growth greater than exponential growth, and the level below exponential is polynomial. Yeah, you can sort of see like e to the x over like x squared goes to infinity, right? By L'Hopital rule, because if you take derivative of e to the x, it's just e to the x, but x squared just keeps decreasing in degree, so you get just constant eventually. So you can sort of see exponential growth is way larger than polynomial growth. Okay, so from here we could sort of obviously at 0 is 0. So when x is not 0, what do we know? Like the first derivative is negative 1 over x squared prime, chain rule, right? That's the first derivative, the derivative of negative 1 over x squared prime times e to the negative. And then the second one, is just product rule. But what do we know? Like if you look at this thing, it gets really bad, right? Like, I mean, it's really messy. But what form do our derivatives have, right? Obviously, it's very hard to calculate the derivatives in this case, because product rule. Here you have one term. The second derivative, product rule, gives you two terms, and then you see the third derivative, product rule, will give you four terms, right? So not good. So, but you see here, if you see how product rule, every derivative via product rule, I guess with some chain rule, but is sums of elements of the form, because derivative of this and this and this is just a higher power of x in the denominator, right? Times some, I don't care about the constant, it's just some higher power of x on the bottom, right? Like derivative of 1 over x squared is like something over x cubed, right? So it's of the form c over x, where c is a constant, times e to the negative 1 over x squared. Yeah, it's sums of elements of these forms, right? Okay, so let's calculate g1, gn at 0. Right, so g1 at 0, let's do that for practice. This is limit x goes to 0. G prime at x, sorry, not g prime, g of x minus g of 0 over x. G of 0 is 0, right, by assumption, right here. So it's just e to the negative 1 over x squared over x. Yeah? Sorry, limit. Okay, so this is, if you like, yeah, I could bring it to the bottom. But so x goes to 0, but e to the 1 over x squared goes to infinity, right? Because 1 over x squared goes to infinity when x goes to 0. And exponential grows faster than polynomial. So this thing will go to 0, yeah? And it actually holds true, you just use induction. Induction, so assume gn of 1 is 0. So, so here the base case is for n equals 2, right? So you assume gn minus 1 is 0, 0. Then gn at 0 is limit x goes to 0, gn minus 1 of x minus gn minus 1 at 0 over x minus 0, right? By induction hypothesis, we assume gn minus 1 at 0, 0. So this is Yeah. Now this is why I wrote the calculation. This thing is, again, if I wrote above, it's sums of elements of the form of this form, right? So let me just, right? So if each term in the sum goes to 0, then the sum goes to 0, right? So it suffices to just take a term that looks like this. So here, this is, you know, we want to find limit x goes to 0, where gn minus 1 of x is something of the form c over x to the k times e to the negative 1 over x squared over x. And if you write it out, this is just c over x to the k plus 1. But same argument, right? This is polynomial. This is exponential, yeah? I mean, this thing will be 0. So you sort of see that the derivatives are all 0 for this function. Now, why is that a problem? Let me ask you all, what is the Taylor series then? For after this calculation at 0, right? Centered at 0. What is the Taylor series representation for this? Does everyone, let me ask. So again, let me remind you, g of x has Taylor series, you know, representation given by sum gk at 0 over k factorial x to the k, right? So what is this series is my question. What did we just calculate? We calculated gn at 0. What is it? So what is this series? Yeah, it's just the 0 series, right? Because every term is 0. All coefficients 0, right? We calculated it above are 0, right? I mean, we did it by induction, yeah. So basically, g of x has Taylor series 0. So in this case, you know, does g of x equal its Taylor series? Is just the question. Is g of x 0 for all, right? And you can see that it's only equal to its Taylor series at 0, right? Because when you're not 0, you're whatever this is, right? E to the negative 1 over x squared. So g is only equal. So g of x is only equal to its Taylor series rep at 0. Yeah, nowhere else. So this sort of, for people interested, you know, we talked a lot, right? But we have functions, and then we move to continuous functions, right? And then we move to differentiable functions. And then we have infinitely differentiable functions. And it turns out, if you think this is nice enough, it's not, right? Because all the functions above the is infinitely differentiable, right? Like gn of 0 was 0 for all n, and gn of x is just some of elements of this form, right? So g of x is certainly infinitely differentiable, right? When you're away from 0, it's just a bunch of product rules, and at 0 you're 0. Yeah, like so these functions, but you see it's not nice enough, right? So and then there's the next step would be they're called holomorphic so analytic functions. So if you want to learn more about this, so these are series, infinitely differentiable, obviously. So they're all subsets, right? So continuous functions is a subset of functions, subset, subset, and this is a subset of this. So series that are infinitely differential, but it's function that is infinitely differentiable, but also equal its power series rep, its Taylor series rep. So there's a whole theory studying these functions. If you want, take complex analysis. If you're interested, they studied holomorphic analytic functions. So anyhow, for those interested. But okay, that concludes. So your quiz is on Taylor series, yeah. So I mean, really, I won't test you on Newton method. You know, it's just just questions about Taylor's theorem. Yeah, just make sure you know like the formula FK at 0. Make sure you know Taylor's theorem and then like just this formula, right? So it's on Canvas. Yeah, it's on Canvas. 30 minutes. I think it's like 3 questions again. Oh, yeah. Okay. Yeah. So in the ones I did, they were bounded by like a number, right? So it could be it's bounded by some. It depends on n. The bound depends on n. But as long as the limit goes to 0, as long as the n factorial wins, you're good. Right. So you sort of see like the problem here was you're near 0, the g of x blows up. That 1 over x squared kills it. Right? It's not bounded. Yeah. Okay.